Hi everybody, today we're going to solve a graph question from LeetCode, number 1254, number of closed islands. This question is very similar to the number of islands question, but with one additional requirement. So the question says, given a 2D grid consisting of zeros representing lands and ones representing water, an island is a maximal 4 directionally connected group of zeros, and a closed island is an island totally all left, top, right, and bottom, surrounded by ones. And then we should return the number of closed islands. For this example, you're given a 2D grid with zeros and ones, islands of 4 directionally connected zeros, top, left, right, and bottom, and closed islands are completely surrounded by ones, and you should count the number of closed islands. For this example, the total number of closed islands would be 2. So you're given this grid, this 2D matrix, and you should return 2 as the output, because this grid has 2 closed islands. So let's manually check the number of closed islands based on this example. We can see that we have 4 directionally connected zeros here, so we mark that as a potential island. That's this, this, and this. So they're connected at the top, at the left, at the bottom, and at the right. So 4 directionally connected zeros is a potential island, and a closed island is one that's completely surrounded by ones. So we can see that this island is also completely surrounded by ones. So this is a closed island. We can also see another instance of zero here. This is a lone island with just 1 0, and that's something you might want to clarify with your interviewer. But an island with just 1 0 is valid, at least for this example, and it's completely surrounded by ones, so it's a valid closed island. So let's mark that. So this is a lone island with just 1 instance of 0, which you might want to clarify with your interviewer, which is completely surrounded by ones, here, 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 so it's a valid closed island. We do have other instances of zeros that could potentially be closed islands. For this example here, this one at the top, also not a closed island because it's not completely surrounded by ones. I'm not also sure if it could be a valid island because it's not 4 directionally connected zeros, just one not at the left, right, and it's only connected at the top and at the bottom. So might be a potential island, but not a closed island because it's not completely surrounded by ones. It's only surrounded by ones on the left side. So how do we solve this question? The first thing we should note is that we first of all have to determine whether something is an island before checking if it's a closed island. Any 4 directionally connected series of zeros could be a closed island. So when we encounter a particular instance of 0 in the 2D grid, as you know, I'm going to be using the words grids and matrices interchangeably, but just know they mean the same thing in this context. So when we encounter a particular instance of 0 in the 2D grid, we can proceed to run a depth-first search on its 4 neighbors to see if we can get a series of directionally connected zeros. While doing the depth-first search, if we encounter a 1, we stop traversing that path and keep traversing other paths. If we have fully exhausted all the paths without going out of bounds, then we know that this is a valid closed island because we exhausted all the paths and then we encountered ones without going out of bounds. If we ever go out of bounds without seeing a 1, then it's not a valid closed island. So I'm going to do a quick simulation of how this would work. So we're traversing this 2D matrix and we encounter an instance of 0. In this case, let's say we encounter this instance of 0. So when we encounter this instance of 0, we then proceed to run a depth-first search and check for all its 4 neighbors. So we run a DFS here, DFS here, DFS here, and here, and here. So if we encounter a 1, we don't actually stop the DFS completely. We just stop traversing that path and keep traversing other paths. So for this one, we've encountered a 1 here. So we stop traversing this path, we encounter 1 here, stop traversing this path, encounter 1 here, we stop traversing this path. But notice that the path on the right, this path, has a 0 to it. So in this other 0 that we encounter on the right, we're going to keep traversing its other neighbors. We run a DFS here for its other neighbors, run a DFS here, We don't run a DFS here because we're going to have a case that checks for that since we've already checked it. Run a DFS here and here. So at the top, we see that it's a 1, so we stop traversing this path and then keep traversing its other paths. The other paths have another instance of 0, that's this one here. So we proceed to run a DFS on its 4 neighbors. So that's this one, this one, this one at the top. We don't go to the left because we've already gone through it. We're going to have a check that checks for that. And then this one has an instance of 1, so we stop traversing. And then we come to this other guy here. We also do the same thing. We go to its 4 neighbors, which is top, right, left, we don't check, bottom, we check. And then we've encountered all of them have a 1, so we stop this path, stop this path, stop this path, and then stop this path. But notice that we already have other depth first searches running on these paths that have zeros that we haven't checked, the bottom neighbors, the left neighbor, and then we'll do that for this path as well. So when we come here, it's an instance of 0. We check its 4 neighbors. This also has an instance of 1 at its bottom neighbor, so we stop this DFS. We stop it here also, and then we do the same thing for its other neighbors, which is this one, and then we come down. You kind of get the idea. We get a 1, and then we go to this other guy, it's a 0, so the guy is a 0, and then they both have 1s at the bottom, so we stop here, stop here, stop here. So this is it. After we've completely exhausted all the paths, and then we've encountered 1s without going out of bounds, in the 2D grid, then we know that this is a valid closed island. So this is how you solve this question. As always with these types of questions, we need to mark the cells that we've visited so we don't count them again. If not, we're going to have the risk of running into a potential cycle, and we don't want that. So how we're going to do this is to change the value of zeros that we've already seen as part of a series to a 1, so we don't get to that again. So for instance, when we've encountered this 0 here, we change its value to 1. This is going to be messy. We change its value to 1. So when we're on this path and we're checking its 4 neighbors, we check to the left and we see, oh, this is a 1, so we don't check it. So after encountering a 0 in a particular series, we have to change the value to 1 so we don't come back to it again. And we're going to do this for all these zeros in this island. I hope this makes sense to you. And now we're going to proceed to the time and space complexity. The time complexity for this algorithm would be O of n in the average case, since we're going through all the cells in the grid. In the worst case, it could potentially go above that because we can also do potentially n amount of work for the DFS, and while doing the iteration, traversing the matrix, we could also do n amount of work, but that's in the worst case. For instance, consider like you have a huge 2D grid of like just 1s on the edges, on all the edges, top, left, right, and bottom, and then zeros in the middle, completely filled with zeros in the middle. What you'll find is when you encounter a particular instance of 0 in the middle, you're going to potentially do n amount of work on the DFS, and you're also going to go into the iterative approach while you're iterating through to check for zeros. Now you're not going to hit the DFS again, but you're still going to check whether, because we're going to change all the zeros to 1s. So when you're going back, you're going to check whether it's a 1 or it's a 0. You're not going to hit the DFS again, but you're still going to do that check. But in the average case, it's O of n. In terms of space complexity would run in O of d, because we're going to have a recursive DFS search which would store frames on the call stack, and the number of frames in the call stack would be as much as the deepest path. So we'll say space complexity is O of d, where d is the depth of the deepest path. So that's it. Let's dive into the code. Alrighty, so we have our closed island function here. It should return an integer. We also have our input 2D grid. So the first thing we want to do is initialize a counter variable. So our initialize count, we set it to 0. And then now we're going to iterate through the 2D grid. This is going to be a nested for loop. So for an I is equal to 0, I is less than, I would say grid.length, and then I++. That's not the way you spell length. I'm going to fix it. And then we say for j is going to go through the columns. So j is less than, I'd say, grid of I dot length j++. And now we have access to the grid of I and j, a particular cell in this grid, and then we can check if that grid is equal to a 0. So if grid of I, j is equal to 0, this could be a potential island. So whenever we encounter an instance of 0, we're going to run a DFS on this instance of 0, because it could be a potential island. Let me fix the length spelling. And then we're here. So we're going to declare like a method that returns, say, a Boolean value if it's a closed island, and then we add 1 to it. So let's say Boolean closed. The method would be called isClosed. We haven't made it yet. We'll make it soon. Bear with me. And then we pass the grid, we pass I and j into it. And then we can check if closed. If this returns true, then we increase the count plus 1. So now let's define the close method that we just used here. So we have a public Boolean is closed. It takes in a 2D grid, takes in a row, and it also takes in a column. So for this, we're going to have a base case that checks. This is our depth first search, by the way. We're going to have a base case that checks if we're not out of bounds. So if row is less than 0, or the value of the row is greater than grid.length, means we're so far down that we're out of bounds. And then we have column is less than 0, means we're so far left that we're out of bounds, or the column is greater than or equal to the grid of row.length, means we're so far right that we're out of bounds. If this is ever the case, then we can just go ahead and return false, because we know that we're out of bounds, so return false. So this is the base case. Otherwise, if we're not out of bounds, then we can check to see if this value is a 0 or a 1. Remember, if this value is a 1, then we can just stop traversing this path. So if grid of row and column is equal to, you guessed it, 1, then we can just return true and stop traversing this path. So we're returning true because we don't want to return false and then stop the whole DFS. And then if it's a 1, otherwise, if it's not a 1, it's going to be a 0. So if it's a 0, then we have to change the value, comments, change the value to 1 so we don't come here again. So we're going to set grid of row and column is equal to 1. So this is a quick check that makes sure that we mark the cell as visited so we don't come here again. I'm going to do more detailed comments for the code that I upload to GitHub, so please check it out. And then we're going to run a DFS on its 4 neighbors. So we're going to have a Boolean variable, we call it bottom. This is going to check for its bottom neighbor. So this is closed. We call the same function. That's why it's called recursion. Have grid, row plus 1, it's going to go at the bottom. And then we have column. This is for bottom. And then we have another variable. This is going to check for the right neighbor. Let's call it right. Is closed. We pass in the grid. We pass in the row, and then we pass in column plus 1. This is going to check for the right, and just call this right. And then we have another one for the left. This is going to be is closed. We pass in the same grid, same row, now column minus 1, and then this is going to be left. And then we have another one for the top, and this is going to be is closed. We have grid, pass in the same grid. Now row becomes row minus 1, and now column remains the same, and this is going to be for the top. So this is going to run 4 DFS searches on its 4 neighbors. And now we want to make sure that all of these return true, because they're only going to return true if they encounter a 1 at the particular path. So we return at the end, bottom returns true, and right returns true, and top returns true, and left also returns true. They're only going to return true if we encounter a 1 before going out of bounds. Awesome. So this is the method, and then here, if it's closed, we call this method, and then we increase count plus 1. Now the only thing we have to do is return count. That's it. That's how you solve this question. Let's run this and see what happens. Awesome, it's accepted. I'm going to submit it. Yeah, it's successful and it's really fast. So that's how you solve this question, guys. I hope you learned something from it. In my experience, asking clarifying questions is a major part of the interview. So please let me know if you want me to include some of the clarifying questions that you might ask for a particular question, like inputs, edge cases in my videos, and I will do that. So comment down below, let me know what you think. So that's how you solve this question. If you like this type of content, please consider subscribing to the channel, share this video around the community, smash the like button for the YouTube algorithm, comment down below if you have something to say, and I'll see you in the next one. Bye bye.